Welcome to today's class. In today's class, we'll be dealing with VSEPR theory, which is valence shell electron pair repulsion theory. Now, VSEPR theory states that molecules or ions assume the shape that best minimizes electron repulsion. In other words, the repulsion between electrons determine the shapes of a molecule or ion. Now, if you look at methane, for example, methane has only bond pairs, so it is easier to arrange the atoms around the central atom in a tetrahedral form. If you look at ammonia, in the other hand, you cannot arrange the hydrogen around the nitrogen atom in a tetrahedral form. The reason is the lone pair electron distort the shape, so the actual shape of ammonia is distorted tetrahedral or trigonal pyramidal. Now, electron repulsion. Lone pair repulsion is greater than lone pair bond pair repulsion. Lone pair bond pair repulsion is greater than bond pair repulsion. So if you have lone pair repulsion, if you have lone pair repulsion is greater than lone pair bond pair repulsion. Lone pair is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. So lone pair repulsion is greater than lone pair bond pair repulsion and is greater than bond pair repulsion. Let's say, for example, we have I3 minus. I3 minus has 3 lone pair and 2 bond pair. So the repulsion between this lone pair, these two lone pair, is greater than the repulsion between this lone pair and the bond pair. Then the repulsion between a lone pair and a bond pair is greater than the repulsion between two bond pairs. So take note, lone pair repulsion is greater than lone pair bond pair repulsion, greater than bond pair repulsion. Now, let's look at electronic shape of a molecule or ion. Electronic shape, which we formally call electron geometry or electron domain geometry, is the arrangement of all electron groups around a central atom in a molecule. This arrangement includes bond pair, single, double, triple, and lone pair arrangement. So if you are talking about electronic shape, all electron regions around the central atom is considered. Let's look at methane, for example. We have C, then we have the 4 hydrogen arranged around the central atom. From our previous classes, you will know that the region of high electron density is 4. If you look at ammonia, you will also notice that the region of high electron density is also 4. Let's look at water. The region of high electron density is also 4. So, in the electronic shape, all molecules with the same region of high electron density have the same electronic shape. You will recall that methane is tetrahedral. The electronic shape of methane is tetrahedral. The actual shape of methane is also what? Tetrahedral, because methane does not have a lone pair electron. So for molecules that don't have a lone pair electron, their electronic chip and their actual chip is the same because we are taking all bond pair. Now, for molecules that have a lone pair electrons, their electronic chip is different from their actual chip. If you look at ammonia, the region of high electron density of ammonia is the same with that of methane. That is, their electronic chip will be the same, which means for ammonia, the electronic shape of ammonia is tetrahedral. But the actual shape is what? Trigonal pyramidal due to the lone pair electron. If you look at water, the electronic shape of water is the same with that of ammonia because they all have the same region of high electron density. Now, for water, the electronic shape will be tetrahedral, but the actual shape will be angular, bent, or V shape. Importance of electronic shape: number one, determines molecular shape, determine hybridization, helps to predict bond angles, explain polarity and reactivity of a molecule. So, those are the four importance of electronic shape. Now, let's look at actual shape. Actual shape. Actual shape refers to the real three-dimensional arrangement of atoms in a molecule, excluding lone pairs on the central atom. It is called actual shape because lone pairs occupy space but are not visible atoms. The observed geometry of the molecule is determined by atom positions only. Now, in electronic shape, we consider all the region of high electron density. Again, let's look at our previous example. If we have methane, we look at the region of high electron density, which is 4. If you have ammonia, the region of high electron density is also what? 4. If you look at water, the region of high electron density is also 4. Now, if you look at methane, you will discover that the region of high electron density, which is 4, is made up of atoms which are bonds pair only. So, the electronic shape of methane will be tetrahedral. The actual shape will also be what? Tetrahedral. Why? Because the actual shape is determined using the atom only, without considering the lone pair. Now, look at ammonia. Ammonia has just 3 atoms surrounding what? The central atom. So, the actual shape is trigonal pyramidal. Trigonal pyramidal, 1, 2, 3. The actual shape is what? Trigonal pyramidal. But the electronic shape is always determined by what? By the region of high electron density. So, the electronic shape will be what? The electronic shape will be tetrahedral. Now, the electronic shape of water is also what? Tetrahedral, because the region of high electron density is 4. Why the actual shape, the actual shape is bent because we have only 2 atoms surrounding the central atom. So, water is bent, angular, or V shape. So, what is the difference? When we are determining electronic shape, we use the region of what? High electron density. But when we are determining actual shape, we use the atom that surround the central atom to determine the actual shape. Now, let's summarize what we are saying. If you look at molecules that are sp hybridized, like carbon dioxide, the region of high electron density is what? Is 2. No lone pair electron. Because there's no lone pair electron, this molecule is sp hybridized because the region of high electron is 2. Now, for carbon dioxide, the electronic shape is linear. The actual shape is also what? Linear. If you look at BF3, BF3, which is what? The region of high electron density is what? Is 3. Hybridization is what? sp2 hybridized. Now, again, the central atom does not have what? A lone pair electron. So the electronic shape is trigonal planar. And the actual shape is also what? Trigonal planar. If you look at sulfur 4 oxide, sulfur 4 oxide is also sp2 hybridized because the region of high electron density is 3. Now, how many atoms surround the central atom? Just 2. But the region of high electron density is 3 because of this lone pair electron. So the electronic shape of sulfur 4 oxide will be what? The electronic shape will be trigonal planar, but the actual shape will be angular. Now let's look at sp3 hybridized molecules like methane, ammonia, and water. They are all sp3 hybridized. Now the electronic shape of methane will be tetrahedral, and the actual shape will also be what? Tetrahedral, because there's no lone pair electron on the central atom. For ammonia, the electronic shape will also be what? Tetrahedral, but the actual shape will be trigonal pyramidal because of the lone pair electron on the central atom. Water, the electronic shape of water will be tetrahedral, but the actual shape will be what? Will be angular bent or V shape. So, in conclusion, molecules that do not have lone pair electrons on their central atom will have the same electronic shape and actual shape. But molecules that have lone pair electrons on their central atom will have different electronic shape and actual shape. Now, this is all we are covering today in the class. Thank you.